everybody. This is Dr. Ritu Singh from Basic Science Department, and today the topic to be discussed is spectroscopy. As per the syllabus of AKTU, this is the second unit of chemistry, engineering chemistry, and this is a new topic for students of BTech first year, because it has not been read, or you have not read this in your 11th and 12th. So by spectroscopy, basically we are going to deal with radiations, how the radiations or the electromagnetic radiations, what is the nature, and when it is going to fall on the molecule, what are the changes which are going to take place. So basically suppose if this is some molecule and an electromagnetic radiation falls on this molecule, then whether the radiation is transmitted, it is absorbed, it is reflected, it is emitted, what are the changes which are going to take place, that is dealt in spectroscopy. Or we can say that when an electromagnetic radiation falls on this molecule, what is the interaction, how the molecule and the radiation, they are going to interact with each other, how the interaction is going to take place, that is dealt in spectroscopy. So in spectroscopy, basically we deal with absorption, transmission, emission, reflection of electromagnetic radiation when it falls on a molecule or when it falls on a material or matter, or the interaction what is the interaction which is going to take place when an electromagnetic radiation falls on the matter or falls on a molecule, that is spectroscopy. Basically spectroscopy is we are going to deal it with in research base. So it is a research topic, because while studying spectroscopy we can tell or we can determine all the information which are required about the molecule. So we are going to see what are the applications of spectroscopy. So first thing in spectroscopy is what we should know is electromagnetic radiation. So as the name electromagnetic, that means radiation is associated with electric and magnetic field, and electric and magnetic field, they are perpendicular to each other. So radiation which is having electric and magnetic field perpendicular to each other, that is known as electromagnetic radiation. Secondly, electromagnetic radiation is having dual nature according to de Broglie's principle. So dual nature means it is having particle nature as well as it is having wave nature. So electromagnetic radiation is having electric and magnetic field associated with it. And this electric and magnetic field, they are perpendicular to each other. And secondly, we say that electromagnetic radiation is having a dual nature. It is having a particle nature as well as it is having a wave nature. Now when some radiation, suppose this is again molecule, when this radiation, any radiation falls on this molecule, the energy is absorbed. Now when the energy is absorbed, or we can say the energy changes are going to take place, or if the energy is absorbed, then electrons, they show movement. So that is reflected in the form of either heat or in the form of energy, in the form of light. So the changes which are going to take place, or when the absorption of radiation takes place, the electrons, they show movement, and the change and the absorption of energy can be seen in terms of either heat, either in the form of energy or in the form of light. And by energy we means electromagnetic radiation is actually energy, it is a bundle of photon as we say. So these are the changes which are going to take place. So basically when an electromagnetic radiation falls on the molecule, the first thing which is taking place is the energy of the molecule is undergoing a change. This change in energy is given by delta E is equal to h mu. So, in one line, if we have to define, then when a radiation, when an electromagnetic radiation falls on a molecule, the energy changes take place in the molecule, and the amount of energy which is going to be changed is given by the equation delta E is equal to h mu. Now, in the molecule, the energy which is going to change is the internal energy of the molecule. We have got two types of energies, not two types but two forms. In one form we say that the two types of energies which are present in the molecule are potential energy and kinetic energy. Kinetic energy when the molecule is moving, and potential energy when the molecule is at rest. But another term to define the internal energy of the molecule is the internal energy of the molecule constitutes, so internal energy of the molecule comprises E translational energy plus E, this is, I should write a short form, so EV, ER and E electronic. So ET is translational energy. EV is vibrational energy. R is rotational energy, and E is electronic energy. So all translational, vibrational, rotational and electronic energy, they comprise internal energy of the molecule. So as the radiation falls on the molecule, the internal energy of the molecule is going to change. So what is going to change? Either the change is in translational energy, or vibrational, or rotational, or electronic, or all the energies are going to change depending upon the intensity of this radiation. If the intensity of radiation is small, then smaller changes are going to take place, but if the radiation is high, the intensity is high, then the changes in energy which are going to take place in a molecule will be larger. So if we talk about all the four forms of energy, translational energy, by translational energy we mean if this is an axis, then to and fro movement of the constituent particle on a particular axis. So constituent particle can be an atom, can be an ion, can be a molecule, depending upon what is under consideration, whether it is an atom, it is a molecule, it is a compound, or it is ions. So what are we working on? So translational energy means to and fro movement on an axis. We have got three axes, x axis, y axis and z axis. Then we have vibrational energy. Vibrational energy means anything is fixed on its position but it is vibrating, that is vibrational energy. Rotational energy means spinning on its axis, and electronic energy means the electron is undergoing a transition from one energy level to another energy level. So these are different forms of energies. So I repeat, whenever a radiation falls on a molecule, the internal energy of the molecule is going to change, and the change in energy is given by delta E is equal to h mu. These four energies, they comprise internal energy of the molecule. Translational energy means to and fro movement. Vibrational energy means vibrating on vibrations on a position. Rotational energy means rotating on its axis, and electronic energy means an electron is undergoing a transition from one energy level to another energy level. Now when there is these energies are there, then we have energy levels, and these energy levels are quantized. So when we have translational energy, we are going to have translational energy levels. When we have vibrational energy, then it will lead to the formation of vibrational energy levels. If we have rotational energy, that is going to lead to the formation of rotational energy levels. And similarly, whenever electronic transitions are there, that means electronic energy levels are there. And all these energy levels, they are all quantized. So by quantization we mean, suppose if this is a structure and the another structure is this. So if I roll a ball here, it will move continuously. This is a classical concept. But if I have a ball here, it is going to fall down here and then it is going to fall down here. So this is the concept of quantization. Every energy level is going to have a definite amount of energy. So by quantization, if we are talking in terms of quantization, that means the energy is not continuous. Every energy level is going to have its own energy. So now we can know the energy, which energy is larger and which is smaller. Now translational energy is important in case of gases, because only in gases the molecules have got so much of freedom to move to and fro on an axis. This type of freedom is not there in case of liquids or in case of solids. Solids, they cannot have this freedom because the molecules are fixed or the force of attraction is very strong. But in case of gases, the force of attraction is very weak. So in case of gases, the molecules have got so much of freedom to move to and fro on an axis. So normally when we are going to study spectroscopy, we are not going to consider translational energy or translational changes. We are going to specify, or we have to specify specifically we are going to consider rotational energy, vibrational energies and electronic energies. So this is how we are going to define. Suppose this is rotational energy. Rotational energy level. If I say the molecule is rotating or spinning on its axis, that means the molecule is simply undergoing rotational changes. It is having rotational energy, and with rotational energy there is formation of rotational energy levels. So transition which is going to take place is only between rotational energy level, and rotational energy or rotational changes are the small changes. So when we are talking in terms of rotation, that means the molecule is only spinning on its axis. No other transition, no other change is going to take place in the molecule. Next, we come to vibrational energies. So this is vibrational energy level. So rotational energy level is present within the vibrational energy level. So when a molecule is vibrating on its axis, so when a molecule vibrate on its axis, it is going to have rotational changes. So one vibrational change, suppose the molecule is moving from here to here, that means one vibrational change is accompanied by large number of rotational changes. Why? Because rotational energy level is present within the vibrational energy level. So one vibrational change is accompanied by large number of rotational changes. And the third, we come to electronic energy level. This is the electronic energy level. So electronic energy level. Now within electronic energy level, we are having rotational levels and we are having vibrational levels. That means if an electron undergoes, even if one electron undergoes a transition from one electronic energy level to another electronic energy level, it is accompanied by large number of rotational changes and large number of vibrational changes. So whenever electronic transition is going to take place, it is not going to take place alone. With one electronic transition, we are going to have large number of rotational changes and large number of vibrational changes. We have a condition where these rotational and vibrational changes can be restricted, but we are going to discuss it later on. So this is the concept about the rotational energies and rotational energy levels, how rotational energies are created, then how rotational energy levels are formed, and when the transition is going to take place between the energy levels, what are the changes which are going to take place. So if a molecule is spinning on its axis, that means it will have rotational energy, and we have rotational energy levels. So that is the only thing change which is going to take place. If the molecule is vibrating, that means one vibrational, when it is vibrating, we are going to have vibrational energy, and then we are going to have vibrational energy level. Now one vibrational change, that means one vibrational transition is accompanied by large number of rotational changes. And the last we come to electronic energies. So when an electron is undergoing a transition from one energy level to another energy level, then one electronic transition is accompanied by large number of vibrational changes and large number of rotational changes. So this is the concept. Next we come to, suppose this is some molecule, and these are the energy levels of the molecule. We can consider rotational energy levels, we can consider vibrational, or we can consider electronic. The concept is going to remain same. So this is N1, this is N2, this is N3, this is N4, this is N5, and this is N6, and so on it is going to go. Now this is the energy level of some molecule. Now if the radiation falls on this molecule, the radiation which is falling is going to have some energy. Now all the radiations which are falling on this molecule are not going to show absorption, or this molecule is not going to interact with any radiation which is falling on this. There is a condition. So the condition is the energy of this radiation should match up with the energy difference here, energy difference between the two energy levels. So when the energy of radiation, energy possessed by the radiation is equal to the energy of the energy difference between two energy levels, only then this radiation can interact with these molecules. And if the energies of the two are not going to match up, then there is no interaction. So again, this is a condition for the interaction between the radiation and the molecule. And what is the condition? When the energy of the radiation which is falling matches up or is equal to, or we say when the energy of the radiation is in resonance with the energy difference between the two energy levels, then the radiation is going to interact with the molecule, otherwise no interaction is possible. So this is again the concept which is going to, we are going to use it time and again. Then we have the whole of spectroscopy is divided into two. One, we are having emission, the other we are going to have absorption. So if we talk about this, the whole of the concept is divided into two. One is emission, the other is absorption. By emission and absorption, what we mean is when the energy is given to the molecule, suppose this is the energy and we give energy to this molecules, the electrons, they gain energy. When they gain energy, they move to higher energy state. anything cannot remain in higher energy state for a longer time. It has to come back to the ground state. Once it comes back to the ground state, it is going to emit the energy which it has absorbed. And when that energy is passed through a prism, we get a pattern, and that pattern is known as emission spectra. So in spectroscopy, we are going to have two concepts. One is based on emission, the other is based on absorption. Emission means when a radiation falls in the molecule, the electrons, they gain energy, they move to higher energy state, and when they move to higher energy state, they are not going to remain there for a longer time. They have to come back to the ground state. Once they come back to the ground state, they emit the energy which is absorbed, and that energy, when it is passed through a prism, we get a pattern, and that is known as emission spectra. The next is absorption spectra. The absorption, or by absorption spectra, we mean, suppose this is a source of light and we are going to place a compound in the path of light, and then this light is passed through a prism. So what happens is, when this source of light is passing through this here, this compound which is present in between is going to absorb some amount of light, and then when that light is passed through the prism, we get a pattern, and this is the pattern, a type of pattern which is obtained. So we are having bright spots, in between we have dark spots. So the portion where we are having dark spots, from that portion this light has been absorbed by this compound. So the pattern which is obtained is absorption spectra. So in this particular discussion, or a discussion about spectroscopy, we are going to deal with different type of absorption spectra. So this is absorption spectra. So the whole of spectroscopy is basically divided into two parts, absorption spectra and emission spectra, and we are going to discuss about the absorption spectra. Now, based on this, we have electromagnetic spectrum based on absorption or emission, or basically absorption. We have electromagnetic spectrum. So if we draw the electromagnetic spectrum, this is the spectrum. And this is a range. So I start with 10 to the power 3, then 10, then we have minus 1, 10 to the power minus 3, 10 to the power minus 5, then 10 to the power minus 7, 10 to the power minus 9, and 10 to the power minus 11. And this is wavelength, which is taken in meters. So if we draw the different ranges or rays, range of rays, then from here to here we have gamma rays. Then after gamma rays, this one is X-ray. Then after X-ray, this is, we are having UV rays. And after UV rays, this short portion is visible range or visible rays. Then after visible rays, this one is infrared rays. So this is IR rays. And after IR, from here to here, we have microwave radiations or microwave rays. And after microwave, from here to here, we have radio waves or radio frequency rays or You can talk in terms of waves or you can talk in terms of rays. So this is electromagnetic spectra. I have taken it in terms of wavelength, and wavelength is taken in meters. So this is the division of absorption spectra, or we have got different type of rays: electromagnetic rays, gamma rays, X-rays, UV rays, visible, IR, microwave, radio frequency waves. So these are different types of spectras. Then after this, after electromagnetic spectra, when we are going to deal with different type of spectra, actually in the present syllabus we have got 4 types of absorption spectra. I am going to introduce those spectra in this particular lecture, and after second and third lecture we are going to take up different spectras one by one. Now in different spectras what we study, or in spectroscopy in general, we have got a rule, and that is a selection rule. Now what is the selection rule? If these are the energy levels, and if I say the electron is present here and it is undergoing a transition, so a selection rule is there to make our study simpler, because if we say that selection, by selection rule means that the electronic transitions are restricted. We are going to restrict the transitions. That means the movement is possible from here to here, or the movement, suppose this is 0, 1, 2, 3. The movement is possible either from here to here, or it is possible from here to here, or it is possible from here to here. Other transitions will not take place. That is the selection rule. That means every spectra is having its own selection rule. Suppose if I say it is delta J plus minus 1. By J I mean J is representation of rotational changes, and if I write V, V is for vibrational changes. If I say the selection rule of any spectra is delta J plus minus 1, that means when I say the selection rule is plus minus 1, that means the electron is going to move only one energy level up. That means 0 to 1, then 1 to 2, 2 to 3. This transition is possible. Other transitions are not going to take place, and by other transition I mean transition from 0 to 2 is not possible. Transition from 2 to 3 is not possible. Transition from 0 to 3 is not possible. Why? Because we have got a selection rule which is plus minus 1. That means the change is going to take place one energy level up, or this is absorption. If the arrow is downwards, this is emission spectra. So absorption spectra, and if the arrow is down, that is the emission spectra, but we are going to concentrate on absorption spectra. Now if the selection rule is 2, that means the transitions which are going to take place are 2 energy levels up or 2 energy levels down. That means 0 to 2 and 1 to 3. This transition is possible, or the other one, this one, this is possible. This is absorption and this transition is emission. Other transitions are not possible. Why? Because we have applied a rule which is a selection rule. So every spectra is having different selection rule. In place of J, if I write V, that means we are talking about vibrational changes, and if I write delta J, that means we are talking about the rotational changes or rotational energy levels, or transition between rotational energy levels. So that is a difference. So it is again an important concept in spectroscopy which will be used time and again in different spectras. So in different spectras we have got different selection rules. So selection rule is basically to know that in particular spectra how the electrons are going to move, what will be the movement of electrons. Then under spectroscopy we have got another law, and this law is Lambert's law. No, actually we have got two laws. One is Lambert's law, the other is Lambert's-Beer's law. So Lambert's-Beer's law is an extension of Lambert's law. So according to Lambert's law, when a monochromatic light falls on the absorbing medium or falls on an absorbing substance or medium, then the rate of decrease in the intensity of the incident light with the thickness of the medium is directly proportional to the intensity of the incident light. I repeat, the rate of decrease in the intensity of the incident light with the thickness of the absorption medium is directly proportional to the intensity of incident light. That is, so Lambert's law, according to this statement, if I write the mathematical expression, it is minus di over dx is proportional to I. And what is this? This is the rate of decrease in the intensity of radiation with the thickness of the absorption medium is directly proportional to the intensity. So I can write it as minus di over dx is equal to ki, and k is the proportionality constant. I can also write it as minus di over I is equal to k dx. If I integrate it within the limits I naught I 0 to x, I get ln I over I naught is equal to minus kx. Now this can be written as I over I naught is equal to e minus kx, or I is equal to I naught e minus kx. So this is one form of Lambert's law. The other form or the other way of solving this equation is, I convert this log into ln into log. So log I naught over I is equal to kx over 2.303. This is a constant which is given by a, or it is given by epsilon. So, and this log I naught over I is a. A is the absorption. So this is written as a is equal to epsilon x. So this is the statement of Beer's law according, Lambert's law. A, absorbance, is directly proportional to the, or is equal to proportionality constant, which is epsilon, and x, which is the thickness. And this x, in some of the books, it is also given by L, which is the path length. According to Lambert's-Beer's law, when a monochromatic light falls on a molecule or falls on an absorbing medium, then the rate of decrease in the intensity of the absorbing medium with the thickness of the absorbing medium is directly proportional to the intensity of the incident light and concentration. So in case of Lambert's law, it was proportional only to the intensity, but here it is proportional to intensity as well as concentration. So I repeat, when a monochromatic light falls on an absorbing molecule, then the rate of decrease in the intensity of the light with the thickness of the absorption medium is directly proportional to the intensity of the light and concentration. So this will be the law, Lambert's-Beer's law or Beer's law. So again, if I write it as dx over di over dx is equal to kic, or di over I is equal to k c dx. Again I integrate it, I get ln I over I naught is equal to kc x. This is with minus sign. Again, if I convert ln into log, then I get I naught over I, which is k cx, and I write it here 2.303. This 2.303 is A, which is your molar absorption coefficient. So log I naught over I is equal to A C x. This is A, which is absorption, and this is your coefficient, which is the molar extension coefficient. So the Lambert's-Beer's law can be written as A. A can be replaced by epsilon also, epsilon C x. So this is Beer's law. So Beer's law is known as, or it is when a monochromatic light falls on a molecule, then what happens is the rate of decrease in the intensity of the radiation with the thickness of the absorption medium is directly proportional to the intensity of incident light and concentration. So this is the whole law. So if I straight write Lambert's-Beer's law or simply Beer's law, then it is equal to A epsilon C x. X, or sometimes we write L, that is the path length or thickness. So this is Lambert's-Beer's law. Then under this spectroscopy, we are going to deal with 4 types of spectra. One is UV spectra. Then I have rotational spectra. And the other is IR spectra. And last is Raman spectra. So in the upcoming classes, we are going to take up these spectras one by one. So if I talk about UV spectra is given by unsaturated compounds. It is not given by saturated compounds. Then we have got a range of UV spectra. It is actually we study UV visible spectra. So this is UV visible spectra. So the range is from 200 to 340, that is visible UV range, and from 340 to 1000 or 700 we have got a visible range. UV spectra is given by unsaturated compounds. Here we are going to study the types of electrons which are present, then what are the transitions which are going to take place, then how many, we have got 2 important types of compounds here, chromophores and oxochromes, and then the applications of UV spectra, and one more principle is there, which is Frank-Odon principle. Then rotational spectra. For a molecule to give rotational spectra, we have got a condition. The condition is the molecule should have a permanent dipole moment. Here we are going to study rotational spectra in diatomic molecules. So we don't go for higher molecules, that means tri or tetra, because then the derivation or the equation becomes very complicated and no result is obtained. So here we are going to restrict our study to diatomic molecules, and here we are going to study the mechanism, how the rotation is going to take place, and then we have got applications. In IR spectra, in case of IR spectra, it is given by the molecules which have got permanent dipole moment, and that dipole moment changes when the molecule undergoes vibrations. So in IR spectra, we are going to deal with how we calculate the degree of freedom, vibrational degrees of freedom in the molecule, and then how many types of vibrations are there or which can take place in the molecules. Then we are going to vibrational spectra. Actually IR is a vibrational changes are taking place, but with vibrational we are having rotational changes also. So we are going to study rotational change only, then vibrational changes only, and third spectra we are going to deal with vibrational and rotational changes, and then we have got applications of IR spectra. Under IR spectra, we are going to consider a molecule to behave as a simple harmonic oscillator, then what are the changes which are going to take place, and when the molecule is not behaving as a simple harmonic oscillator, that means there is no harmonicity, then what are the changes which are going to take place. Then at the last we have Raman spectra. In case of Raman spectra, it is given by the molecules which have got, or where there is a change in polarizability. Then when a photon falls in a molecules, then we have got a Rayleigh scattering and we have got Raman scattering. Then individually we are going to deal with the rotational spectra in Raman, vibrational spectra in Raman, and then rotational vibrational spectra in Raman, and then dealing with certain examples of Raman spectra. Then if I come to applications, so we discuss some applications about spectroscopy. So spectroscopy basically is going to tell, or it gives information about the whole molecules. Then what is the molecular symmetry? So it will give information about the molecular symmetry. It is going to tell about us about the molecular bond length. Then what is the bond angle? It is going to deal with thermodynamic parameters. It is going to deal with thermodynamic parameters. Then by spectroscopy we can determine whether the molecule is a saturated molecule or it is an unsaturated molecule, and that is dealt by UV spectra, because UV spectra is given by unsaturated compounds. So if the molecule is giving UV spectra, that means it is an unsaturated compound, and if it is not giving UV spectra, that means it is a saturated compound. So we can determine whether the molecule is saturated or the molecule is unsaturated. Then we can also determine whether the molecule is having a double bond or it is having a triple bonded it is double bonded compound or it is a triple bonded compound. Then we can study or we can calculate the dipole moment. So here dipole moment, we can calculate dipole moment by rotational spectra. So in rotational spectra we have got a short derivation from which when the equation is derived we can calculate the dipole moment. Then in from spectroscopy we can determine the impurities. If the impurity is present in the molecule or not. Suppose we are dealing with UV spectra, and if it is having an impurity, then if the impurity is present, then because of the impurity an intense band is obtained or a peak is obtained. So if we are getting a very intense band or a very intense peak, that means that is because of impurity present in the molecule. Now if we study IR spectra, then for every impurity an extra peak or an extra band is obtained. So we can identify that that particular molecule is having an impurity. Then we can also, by spectroscopy, we can analyze what is the type of hydrogen bonding which is there in the molecule, whether it is intermolecular or it is intramolecular. So hydrogen bonding can be determined by IR spectra. So if it is intermolecular hydrogen bonding, the absorption band is going to diminish with dilution, and if it is intramolecular, then the absorption band is unaffected by dilution. So we can identify what type of hydrogen bonding is present in the molecule. Then we can determine whether the molecule is having center of symmetry or not. If the molecule is not giving IR spectra, but it is giving Raman spectra, that means the molecule is having a center of symmetry. And if it is giving IR and Raman both, that means the molecule is not having center of symmetry. Then spectroscopy helps us to calculate quantitative analysis. And this quantitative analysis is done by Beer's law, epsilon CL. So if we know the absorbance, we know the path length, we can calculate C. C is the concentration. So from concentration we can calculate that means we are calculating the quantity, we can calculate volume, we can even calculate molecular mass or molecular weight from this. So spectroscopy deals with, or it helps us for qualitative analysis as well as quantitative analysis. Quantitative analysis is done by this Beer's law, and qualitative analysis is done by carrying out spectra, then studying the molecules. And secondly, we can also differentiate how many, or we can find out how many degrees of freedom are there in the molecule. By degrees of freedom we mean how many types the molecule can vibrate, or it can rotate, or it can show any kind of movements. So we have got 3 degrees of freedom: translational degree of freedom, vibrational degrees of freedom, and rotational degrees of freedom. So vibrational degrees of freedom we can calculate in case of IR spectra. So in the upcoming lectures we are going to take up UV spectra, IR spectra, rotational spectra, and Raman spectra separately. So this was the introductory lecture of spectroscopy. Thank you.